For decades, the semiconductor industry operated on a simple, predictable model: make individual silicon wafers smaller, faster, and cheaper. But in 2026, the sheer physical weight of artificial intelligence compute requirements forced the industry to abandon that wafer-centric model for a completely infrastructure-centric approach. At NVIDIA's GTC 2026, CEO Jensen Huang laid out the financial reality of this new infrastructure. He projected an astonishing $1 trillion in AI chip demand through 2027. This represents a doubling of the prior year's projection, driven entirely by an unrelenting need for more data center hardware. NVIDIA's Vera Rubin platform functions as a rack-scale AI supercomputer. A single unit integrates 72 Rubin GPUs connected via 6th-generation NVLink switches. NVLink is a high-speed interconnect technology that allows GPUs to share data rapidly within a system. The platform also includes 36 Vera Data Center CPUs and custom storage networking, creating an incredibly dense and power-hungry block of compute. But designing $1 trillion worth of hyper-dense supercomputers on a whiteboard is entirely different from physically building them. This massive spike in demand is actively colliding with severe, real-world physical constraints across the global supply chain. Escalating Middle East conflicts and blockades around the Strait of Hormuz have triggered a domino effect in raw material availability. Essential manufacturing elements like helium gas and gallium, critical for fabricating these complex chips, are facing sudden, severe export risks and spiking costs. Competing nations are moving aggressively to capture the resulting manufacturing flight. India's 2026 budget specifically targets this vulnerable semiconductor supply chain, offering massive 5-year tax exemptions and near-zero import duties to lure desperate chipmakers. The theoretically limitless demand for AI processing power has hit a hard ceiling. It is now strictly capped by the finite realities of physical Earth materials and rigid political borders. Down at the fabrication level, this resource scarcity is forcing foundries to make ruthless choices. The massive floor space and raw materials required to print AI accelerators mean factories have to actively reallocate their production lines away from older technologies. This graphic tracks recent market shifts, showing that Samsung Foundry is actively securing AMD's AI chip memory orders. To accommodate hyperscalers, Samsung has reportedly dedicated over 50% of its sprawling Pyeongtaek facility exclusively to producing base dies for HBM4. HBM4, or High Bandwidth Memory, is a specialized architecture that stacks DRAM chips vertically to vastly increase data transfer speeds. With industry giants like TSMC and Samsung dedicating their most advanced factory space to AI and HBM, a severe capacity vacuum has opened up at the bottom of the market. The mature node chips used in automotive, industrial, and consumer electronics are suddenly starved for factory time. This infographic outlines the direct result: a planned pricing adjustment for mature node foundries. Major players, including UMC, Vanguard International Semiconductor, PowerChip, and China's NextChip, are set to raise their quotes by up to 10% starting in April, citing tightening supply and recovering demand. The global race to build high-end AI infrastructure is actively cannibalizing the manufacturing capacity required to sustain the rest of the consumer electronics market. This exact same fracture is playing out within the memory sector. The insatiable need for data center memory has split the market in two. The world's top memory suppliers, SK Hynix, Samsung, and Micron, are currently routing nearly all of their new capital expenditure into building entirely new lines for 3D AI memory. SK Hynix alone is constructing a $13 billion packaging facility just to keep up with accelerator orders. This animated chart illustrates the brutal math of that pivot. Because production has shifted away from conventional DRAM, the memory used in standard smartphones and PCs, supply has plummeted. As a result, consumer DRAM prices have surged a staggering 180%, and the industry does not expect a quick correction. Current forecasts project that these memory wafer shortages will remain suppressed and persist all the way until the year 2030. The extreme profit margins of specialized AI memory have broken the supply and demand equilibrium of the traditional consumer market, leaving standard electronic supply chains deep in the red. Even with factory space secured, actually building next-generation AI systems like the Vera Rubin requires abandoning legacy engineering concepts altogether. To achieve the extreme compute density NVIDIA requires, engineers cannot rely on flat 2D wafers. The industry is being forced to adopt true 3D vertical stacking, layering functional silicon directly on top of other silicon. This diagram breaks down the advantages of TSMC's SoIC, or System on Integrated Chips, a method bonding silicon dies vertically. This vertical stacking vastly improves transistor density and bandwidth, and is expected to power NVIDIA's upcoming Rubin Ultra and Apple's M5 chips. But stacking chips vertically introduces a massive blind spot for process engineers. It requires a completely new approach called subsurface metrology. Metrology is the science of precision measurement and inspection, and in this context, it focuses on the hidden internal layers of a manufactured object. Traditional inspection methods rely on optical cameras bouncing light off a flat surface. But when you stack active logic dies on top of each other, surface inspection is useless. Engineers now require advanced metrology solutions capable of probing deep into buried structures to capture microscopic three-dimensional variations before the final package is sealed. And once the silicon is finally stacked and inspected, it has to survive extreme heat. With NVIDIA officially standardizing liquid cooling for its Vera Rubin servers, thermal management is no longer an afterthought for data center operators. Testing for thermal reliability and liquid cooling integration has now been pulled directly into the early stages of the fab process. Semiconductor manufacturing is no longer a localized process of printing tiny circuits on flat silicon. Building the AI stack requires engineering a holistic, three-dimensional thermal and optical ecosystem managed across global supply chains that are already stretched to their absolute limits.